wabarakatuh, and a very good day to Chairman, presenter and all participants of International Symposium on Multidisciplinary Science 2022. So it is a privilege for me to share my research topic which focus on the cellulose extraction from agricultural biomass, which is the rice husk, and to be incorporated with starch-based composite packaging materials. I am Halimatun Saadiah from Institute of Plantation Studies, UPM. Firstly, I would like to introduce our core material used in this study, which is the rice husk that produced during the paddy processing. In most of the Asian and African regions, paddy is a staple food due to its high nutrition and can be found in many varieties, such as long rice, fragrant rice, brown rice, japonica rice, and etc. It is also known as the third largest agricultural commodity in the world. So rice husk is produced during the milling process and being generated approximately 20% of the 500 million tons of paddy produced worldwide. So based on the anatomy of the rice, so rice husk is coating on the seed of the rice and can be separated during the hulling process. So it is considered as the hard material that contains the silica, lignin, hemicellulose, and cellulose, which is our interest in extracting the cellulose for valuable products. Let me introduce our interest component in rice husk, which is the cellulose. It is the structural materials in plants which support the plants. It is a polysaccharide that link with glycosidic linkage. It is characterized by the hydrophilic, biodegradables, and also have the high tensile strength that determines its mechanical properties. With the good mechanical properties makes the cellulose potentially converted into composite materials, packagings, filters, fillers, and also as a transparent sheet. The extraction of cellulose has involved several stages, which currently the cellulose extraction is using the hazardous chemicals such as the chlorine for removing of the lignin, hemicellulose wax, and also can act as the bleaching purposes. So the use of more environmental safe chemicals is rarely documented. Therefore, we want to propose the cellulose extraction using the nitric acid treatment and compared with the chlorine extraction method. So the cellulose extract will then be incorporated in the starch with the target to improve the properties of the starch to be used as the packaging purposes. In the first step, rice husk will undergo separate treatment process with chlorine and nitric acid treatment to remove the remaining lignin, hemicellulose, wax, and other impurities. So we can see the different color of the cellulose extract, which is if treated with the chlorines, it's yielding long fiber white in color, whereas for nitric acid treatment is yielding slightly brown with short fiber in colors. So both cellulose will be further treated with 30% of the phosphoric acid for surface modification process, with the target so that the cellulose and starch will be able to bind together. And after that, both will undergo casting process at lower temperature before the film can be peeled off for analysis of the microscopic, hydrophobic, thermal, and mechanical properties. In the first part of the study, we can see the comparison of the chlorine and nitric acid treatments in terms of the cellulose yield. So after treatment, we can see the increase in the cellulose content was observed for both chlorine and nitric acid treatment as compared to the untreated. And the value is slightly comparable, indicates that the removal of lignin and hemicellulose through this method was significant. The effect of treatment on morphology characteristic of the rice husk was shown in the next figure, and the morphology of the chlorine-treated rice husk fiber was slightly soft with the natural cotton-like, and the particle size approximately 2 mm in size. And as the chlorine also act as a bleaching agent, makes the white color of the cellulose. Meanwhile, in nitric acid treatment, the fiber were in the powdered form with pale yellow in color and more uniform in size. So in this treatment as well, silica also removed, indicated by the empty crater here, which importance in facilitate further treatment of the cellulose. Another important criteria in assessing the efficiency of cellulose extract is the crystallinity index. So cellulose structure is basically comprised of the crystalline and the amorphous region. The crystalline structure is where the water was excluded almost completely from the crystalline region in cellulose, and cellulose usually much slower degraded due to the crystalline structure. Whereas for amorphous structure, it is more readily available uh, and readily being attacked by other reactants, and it is also regarded as more reactive form of the cellulose. So the crystallinity index of the chlorine and nitric acid treated rice husks were high as compared to the untreated, uh, as most of the amorphous region has been removed. So the action of the hydrogen ion from the acid has been penetrate into the amorphous region and cleft the bond, release the crystallite, produce high crystallinity. So the crystallinity give the rigidity and strength to the particle and suitable for composite packaging. As for the thermal properties, we can see the weight fractions of the raw rice husk residue showed the lower weight loss due to the silica content, and most of the lignin and hemicellulose still remain in the fibers. But the removal of the heat-sensitive hemicellulose, which also has the lower decomposition temperature, indirectly increased the thermal stability from 334 to 346 and 339 degrees C of the treated rice husk. So we can say that the proposed extraction methods of using nitric acid and was incomparable with the current chlorine methods in cellulose treatment. In the second part of the study, surface modifications of the cellulose with phosphoric acid is required to facilitate the reinforced starch process, as we targeted to improve the film hydrophobicity, mechanical properties, and its quality. So the wettability properties of the neat starch and starch cellulose film were determined by contact angle analysis. So wettability is the ability to withhold the liquid on the surface of the composite film, which also determine the hydrophobic or hydrophilicity properties of the film. So the contact angle of the starch cellulose composite was lower than neat starch before the surface modification due to the presence of the hydroxyl group. But after the treatment, the contact angle increased to 85 to and 88 degree, as the hygroscopic change in starch cellulose was resulted from the substitutions of the hydroxyl groups by less polar group of the phosphate. So we can see slightly improved in the hydrophobicity properties of the starch cellulose composite after the treatment process. Meanwhile, for mechanical properties, improvement of tensile strength from 3 megapascal to 22.9 and 17.4 megapascal was observed, attributed to the surface modifications of the hydroxyl groups that increased the compatibility of the treated cellulose with starch matrix. So the dispersions of the cellulose in the starch matrix produce more compact structure, as the cellulose reduced the strong attractions of the hydrogen bond within the amylose and amylopectin molecules in the starch network. In determining the opticals and UV shielding properties, the transparency analysis using spectrophotometer transmittance is carried out. The transmittance is the fractions of the incident light which is transmitted. In other words, it is amount of the light that successfully passed through the substance and come out another side. So transparency of the packaging material is depending on the diffuse transmittance of white and narrow angle light scattering, which play a role in customers' visual inspections and appearance of the products. So for UV analysis, it can be divided into three range, which is the UVA, UVB, and UVC. So NITS touch film had high transparency with low ability to absorb the UV light, as it exhibit the high UVA, B, and C transmittance as compared to the starch cellulose composite film. So the deficiency of to absorb the UV light can be a problem, as the UV light can cause formations of the free radicals and the agings of the inside materials that might induce chemical reactions and deteriorations of the color. Although the additions of the cellulose had decreased the film transparency, they provide the UV protection without compromising their transparency. So it was still possible for us to see through the composite films, which show the potential of cellulose to be used as the UV shield for starch film packaging. So as the conclusion, this study proved the feasibility in extracting of cellulose using environmental extraction methods with high potential for further use to increase the performance of starch as packaging materials. So with that, I end. Thank you.